Hi, in this video, we want to take a look at hypothesis testing for linear models. Okay, so we're talking about linear regression. We have a situation where I have a theoretical model. So, this looks a lot like something you see from college algebra, where we have independent variables are predicting a dependent variable, and we're using coefficients. So this is a degree 1 polynomial to model the target variable. Okay, and here is our error term, epsilon. All right, and we're going to make the assumption that epsilon is normally distributed with a mean 0 and constant variance with respect to the x's. Now, what we do, we take our data and we do our best guess at what the model structure is. Okay, so this beta sub 0 hat is my data's best approximation of this beta 0. Beta 1 hat is my best approximation of beta 1. All right, so remember, anytime I'm working with data, I don't actually know the situation. Because of subject matter knowledge, I believe that this is the correct equation. Well, I don't know what the actual betas are. I know what the variables are, but I don't know the betas. So I do my best that I can do with my data to estimate what the coefficients are. And that's where we get our linear regression model. Okay, so let's go ahead and work through an example. We're going to use the life cycle savings data set from R's data sets package. This is a base package with R. So if you have R on your machine, you have this data set available. And I'm just going to go through and we're going to say that SR depends on population 15 DDPI, population 75, and DPI. Okay, and let's go ahead and let's make a reduced model. So here we're going to call this the full model. You see how it has 4 predictor variables in it, and the reduced only has 2, so I'm reducing it down. And then for an interaction model, I'm going to include an interaction term tacked on to the reduced. Okay, so the first thing I want to know is, in my model, is there something bringing value? So I'm not, this is very global, this is overall. Is there one or more predictor variables bringing value? Okay, so I want to know, is there something good here? All right, so I'm going to run a hypothesis test. My null hypothesis is that all of those coefficients of the x's are equal to 0. All right, so in this situation, if all of these are equal to 0, boom, right there, you see that. If all of the coefficients of an x are 0, then in that equation I had up top, then that means that, if I scroll up, if that's 0, that's 0, all of the subsequent betas are equal to 0, then my model is y is equal to a constant plus the error term. Well, that means that all these x's are useless for the purpose of figuring out information about y. Okay, so if the x's are useless in understanding y, then I don't want to include them because it's just noise. It will distract me from what's going on. And so the null hypothesis is that they're all equal to 0. And the alternative is that one or more are not equal to 0. Okay, so now this says one or more does not equal 0. It doesn't tell me which ones. It could be 1, could be 2, could be all of them. We don't know at this point. But this is just a first way to get going. Now, remember, in hypothesis testing, equal signs always go with the null hypothesis. The reason, well, one of the reasons for this is that I need that equal sign to define what the probability distribution is going to be. Okay, so what we're going to do, we're going to use an F statistic to figure this out. And in R, how I get this is I use the summary function. I just pass my model in there. And so my output, at the very bottom, I have my F statistic. All right, I can see the F statistic is 5.8. My degrees of freedom are 4 and 45. And my p-value is 0.008. That's pretty small. All right, so here, off of this hypothesis test, I reject the null hypothesis in favor of the alternative. So here I reject the null in favor of the alternative. I conclude that one or more of the slopes are not equal to 0. Now, that just says one or more are not equal to 0. I don't know which ones are the good ones. Okay, so let's go in a little bit deeper. So which predictor variables are bringing value? Okay, well, for this hypothesis test, what I'm going to do, I'm going to run the hypothesis that a particular coefficient is equal to 0, and the alternative is that particular coefficient is not equal to 0. So it's a two-sided test. And to do this, this is very similar to a two-sided t-test. Once again, I use the summary function, but this time, so previously we looked at the F statistic at the bottom. Now I'm looking at the coefficients. So here I'm checking to see, is population 15 equal to 0? Here's my hypothesis test for that. Is DDPI coefficient equal to 0? Here's my hypothesis test. POP 75, there's my hypothesis test, and DPI. Okay, so here, population 15, that's a rather small p-value, so I conclude that it's not equal to 0. I'm going with the alternative. DDPI, all right, that's less than 0.05. I conclude it's not equal to 0. Now, POP 75 here, that's greater than 0.05. So by that criteria, I would fail to reject the null hypothesis. I conclude that POP 75 by this measurement is equal to 0. And I conclude that DPI is equal to 0 because the p-value is greater than 0. Now, something I did when I was preparing for this video, I sorted the order of the coefficients by the p-value. So that's why they're in order like this. I did that to make it easier to interpret. But in general, it's going to be all mixed up. Whatever order you put it in is the order that the p-values will appear in. And we can see that we're using a t-test. And here we're using standard error. And here's the actual coefficient value estimated. Okay. Now, the next question is, should I use a simpler model? Well, I could see that 2 of the coefficients look like they're not 0. 2 of them look like they are. Should I go ahead and get rid of the ones that are hypothesis test equal to 0? Will I lose informative value in terms of an F statistic evaluation? All right, so we've got 2 ways to evaluate, or 2 ways to compare models. So we have like a sequential version where we take the point of view that we're adding coefficients or terms to the model sequentially, and I want to check sequentially how the current model compares to the previous. Or I can take 2 particular models I'm interested in and compare them. So for this one, for the sequential model, I'm going to run ANOVA. All right, so in R, what's going to happen is that this hypothesis test is asking, should I add POP 15 to the constant model? So the default is, for this hypothesis test, we could think of it as the null hypothesis is we should go with the constant model. So there's no x's at all. Now, this shows this is very small, so I reject the null hypothesis. I conclude that I should add POP 15 to the constant term in the model. Now I go to the next one. This is asking, should we add DDPI to the model with a constant and POP 15? Okay, well, that's a small p-value. I conclude I should add DDPI to the model that has a constant and POP 15. This hypothesis test is checking to see, should we add POP 75 to the model with a constant, POP 15, and DDPI? Okay, and so here I fail to reject the null hypothesis, and so I conclude that adding POP 75 to the model with these 2 predictor variables and the intercept, I'm not going to get more informative value by adding this variable. And so here, once I stop, I don't even consider adding this. So by this criteria, that reduced model with POP 15 and DDPI as our predictors is the better model to use. Now, let's go a little bit different. Let's go ahead and compare two specific models that we're interested in. So if I run ANOVA and I give it two different models, it will run a test for us checking to see. The null hypothesis is that the two models are equally informative. The alternative hypothesis is that one is more informative than the other. Well, it's set up so that all of the predictors in reduced are also in the full. So if there's a better one, it's going to be the full model. And so if they're equally informative, I'm going to fail to reject the null hypothesis. If it looks like the more complicated model has more informative value, then I'm going to reject the null hypothesis. So here we fail to reject the null hypothesis. We conclude that the reduced model is equally as informative as the full model. And so if two models are equally informative and one is simpler, I want the simpler one. Now we can get into more advanced linear hypothesis tests. Here we're going to use the CAR package and linear hypothesis function. And there's several ways to do this. So here in this version, I'm checking to see, I'm running a hypothesis test to see, you know what, is it reasonable for the intercept to be 29, the first coefficient to be negative 0.5, the second one to be positive 0.5, negative 2, and then 0. All right, so what I did was I went up, I'm going to scroll up, go to the, so here are the estimated values. I rounded this to 29. I rounded that to negative 0.5. I made that 0.5, not rounding. I made this negative 2, and then I made that 0. And because those are simpler numbers, right? So if I'm explaining to people, I don't want to go around giving, you know, what, 1, 2, 3, 4, 5, 6 decimal places. Like most people are not going to enjoy looking at 6 decimal places. So I just lopped them off. And now, did I lose anything? I want to know, do I basically have a very comparable model in terms of informative value? And so I'm running this linear hypothesis test. And what I have to do, I put in a vector for the right-hand side. And in this vector, I just put it in the same order as I have in the summary statement. And so here they are. And so now I run the hypothesis test, and I can see that it's once again an F statistic, and we fail to reject the null hypothesis. So I conclude, so this hypothesis test concludes that you know, intercept equals to 29, pop 15 equal negative 1/2, DDPI equal to 1/2, pop 75 equal negative 2, and DPI equal to 0 is, you know, is equally as informative as the model that was fitted as closely as possible to the data. Now, there are situations where the F statistic doesn't work out for us. And so what we're going to end up doing is we're going to use a chi-square distribution using some asymptotics. So asymptotics are a theoretical situation when things go off to infinity. So here, if I want to change the test, going from the F distribution to the chi-square distribution, I just put test equals chi-squared. For theoretical reasons, this might be advantageous over the F distribution. And so I run the same test, and you notice that once again, I failed to reject the null hypothesis. So these coefficients are equally informative as the ones that were fitted to the model using the data. Now, next type of hypothesis test I can run is that I want to check to see particular equations of the coefficients. So let's just say, for just hypothetically, I'm interested in the equation 5 times population 15, 5 times the DDPI plus 1 equals to 1. Do I believe that this is a correct equation for all my coefficients? Okay, well, I would like to run that hypothesis test. Well, what I'm going to do, I'm going to use linear hypothesis in the CAR package once again. And when I run it, and you notice I'm using the reduced model, I get a small p-value. I fail to reject the null hypothesis, and so I conclude that this is a correct equation. All right, well, that's all I've got for you. Take care and goodbye.